Hello friends, welcome back to my YouTube channel. This is part number 21 of my discussion on adsorption, and in this I will be discussing a numerical example that is based on the application of the Freundlich Adsorption Isotherm to multi-stage countercurrent adsorption operation. In part number 20, I had discussed how we can apply the Freundlich adsorption isotherm to a two-stage countercurrent operation. So based on that discussion, today we will solve one numerical that will tell you how you can apply the Freundlich adsorption isotherm to a two-stage countercurrent operation, and then by applying the Freundlich adsorption isotherm, how can you find the quantity of adsorbent that is required in the operation. Plus, you'll also learn how to find the minimum quantity of adsorbent that can be used in the operation. So let us start the discussion. Okay, let us first look at the numerical statement. Let me tell you, I am considering the same numerical which I had solved in part number 19. But in part number 19, I had used graphical method to get the quantity of adsorbent that is required in the operation. So in today's discussion, I will be using the Freundlich adsorption isotherm to find the quantity of adsorbent that is required in the operation. So let us first look at the numerical statement. So you have a solution of washed raw cane sugar, 48% by weight, is colored by the presence of small quantities of impurities. It is to be decolorized at 80 degrees Celsius by treatment with adsorptive carbon in a contact filtration plant. So you have a sugar solution that is containing 48% by weight of sugar in it, but it is colored by the presence of small quantities of impurities in it, and the objective is to reduce these impurities. So for that, the solution is to be decolorized at 80 degrees Celsius. So the operation is carried out at constant temperature. How it is done? By treatment with adsorptive carbon, and this is done in a contact filtration plant. So basically, adsorption is to be used to reduce the color impurity in the colored solution, in the sugar solution. The data for an equilibrium adsorption isotherm was obtained by adding various amounts of carbon to separate batches of the original solution and observing the equilibrium color reached in each case. The data with the quantities expressed on the basis of the sugar content of the solution is as follows. So data is given to us. So we have different values for kg carbon per kg dry sugar, and then we have different values for percentage color removed. So the data is given to us. This is the data that is given to us. So this equilibrium data, how it was generated? It was generated by adding various amounts of carbon to separate batches. So the original solution, it was taken in separate batches, and to each batch, a particular amount of carbon was added to each batch. So you can see the amount of carbon added. The amounts of carbon added, they are given on the first row. And after adding various amounts of carbon, the percentage removal of the color that was obtained, that was observed, or that was reported. So when 0.005 kg carbon per kg dry sugar was added to a batch, then 47% color impurity was removed. when 0.01 kg carbon per kg dry sugar was added to the batch, 70% color was removed. So the data is given in this form. The other thing that they have mentioned in this case is the quantity is expressed on the basis of sugar content of the solution. So solution which is containing sugar and water, 48% of sugar in water. So here this quantities are expressed on the basis of kg, basis of sugar content that is present in the solution, and we have to consider this while solving the numerical. You will shortly know how we are going to use this information. Let us move ahead. Okay, further they have given this information. The original solution has a color concentration of 20 measured on an arbitrary scale, and it is desired to reduce the color to 2.5% of its original value. So the original solution, it is having certain color concentration, and it is measured on an arbitrary scale. And on this scale, the concentration of color in the original solution, it is 20. And this is to be reduced to 2.5% of its original value. That is, it is to be reduced to 2.5% of 20, the original value. And for this, we are supposed to first convert the equilibrium data to capital Y, which is defined as color units per kg dry sugar, and capital X, which is defined as color units per kg carbon. You have to note over here how capital Y is defined in this case. So we are defining it on the basis of dry sugar. So instead of defining capital Y as color units per kg solution, we are defining it as color units per kg dry sugar. And why are we doing this? Because the quantities that are given in the equilibrium data, they are expressed on the basis of dry sugar in the solution. So that's why capital Y is defined in this way, color units per kg dry sugar. And capital X, as usual, it is described as color units per kg carbon. So first task is to convert the given data to this form, to capital X and capital Y. And the second task is we have to check if the converted data follows the Freundlich adsorption isotherm equation, which is of this form, capital Y is equal to m into capital X raised to n. So you have to check whether the X and Y values, they follow this equation. If the values follow this equation, we have to get the values for constants m and n. M and n in this equation, these are constants. So if this equation is applicable, we have to find the values for m and n. Then for a two-stage countercurrent adsorption operation, we are supposed to find the quantity of adsorbent that is required per 1000 kg of the aqueous solution. And for the same case, we are supposed to find the minimum quantity of adsorbent that can be used. So we have many tasks to perform, or tasks to complete in this case. First, we have to convert the equilibrium data to the required form. Then we have to check whether the converted data is following the Freundlich adsorption isotherm equation. If it is so, we are supposed to find out the values for these constants m and n. Then for a two-stage countercurrent adsorption, if the feed solution is 1000 kg, then what is the quantity of adsorbent that is required in the operation? And then in this case, what is the minimum quantity of adsorbent that can be used? So I hope you have understood what is given in the numerical statement and what are we supposed to find out, what are we supposed to calculate. So let us begin. Let us move ahead. As usual, first we will list the data that is given to us. So you have an aqueous solution containing a color impurity. So the quantity of aqueous solution, as per our notation, we denote it as L0. So L0 in this case is mass of dry sugar plus mass of water plus color impurity. And this quantity, we are supposed to handle 1000 kg of such a solution. 1000 kg of sugar solution that is containing color impurity in it. The objective, what is the objective? The objective is to reduce the color impurity by adsorbing it on adsorptive carbon, which is the adsorbent in this case. Only the color impurity is adsorbed. So out of the three components, sugar, water and the color impurity, only the color impurity is getting adsorbed. So that means the solution, which is dry sugar and water, the solution, it is not adsorbed. The equilibrium data that is given to us, in the equilibrium data, the quantities are expressed on the basis of sugar content. So therefore, in this case, ELS is not kg of solution. ELS is the kg of dry sugar that is present in the aqueous solution. So that is what you have to remember in this case, since the equilibrium data is given in that form, kg carbon per kg dry sugar. So in this case, ELS, the component that will not be adsorbed, is the dry sugar or sugar content of the solution. So therefore, in this case, ELS is kg of dry sugar in the aqueous solution. So sugar content of the solution is given to us. The aqueous solution is containing 48% of sugar in it. So we get ELS. So ELS would be 0.48 times of L0, which is 1000. So it is 0.48 into L0. That is equal to 0.48 into 1000, which is 480 kg. So I hope you must have understood how we have taken LS, how we have chosen LS in this case. So LS in this case is the quantity of dry sugar that is present in the solution. The solution is containing 48% of sugar in it. 1000 kg of sugar solution is containing 48% of sugar in it. So that's why LS comes out to be 480 kg. So why are we doing this? Why are we taking LS as the sugar content of the solution? The reason is the equilibrium data is given on the basis of sugar content of the solution. So I hope this is clear to you. Let us move ahead. Further, the equilibrium data, it is given in this form. We have different values of kg carbon per kg dry sugar, and then we have different values of percentage removal of color. And we are going to use this, or we are going to convert this data to capital X and capital Y. That has to be converted to capital X and capital Y. And the color concentration, it is measured in terms of its intensity. The color intensity is directly proportional to the concentration of the color in the solution. And the color intensity is to be reduced to 2.5% of its original value. So that means in this case, the original value, original concentration of the color is 20. So that itself is capital Y0. So we are saying that initially color concentration is 20 color units per kg dry sugar. So that's why in this case capital Y0 is 20. And this has to be reduced to 2.5% of its original value. So therefore in this case final Y will be 2.5% of capital Y0. So that is 0.025 into Y0. That is 0.025 into 20, which comes out to be 0.5. So in this case, the initial color concentration is 20 color units per kg dry sugar. and it is to be reduced to 2.5% of its original value, which comes out to be 0.5 color units per kg dry sugar. So final Y in this case is 0.5 color units per kg dry sugar. What are the objectives? So based on all the data that is given to us, what are the objectives? First, we are supposed to convert the equilibrium data to capital X and capital Y. Capital Y, as I said, this is color units per kg dry sugar, and capital X is color units per kg carbon. And then we have to check if this converted equilibrium data follows the Freundlich adsorption isotherm. Capital Y is equal to m into capital X raised to n. And if so, we are going to find the values of m and n if y is equal to m into x raised to n is applicable. And then for a two-stage counter current adsorption operation, we are supposed to find the quantity of pure adsorbent that is required per 1000 kg of the aqueous solution. And in the same case, we are supposed to find out the minimum quantity of pure adsorbent that is required. Since we are supposed to use, the meaning is we are supposed to use pure adsorbent. We are using pure adsorbent. So what is the meaning of that? X0 is 0. That is the adsorbent that is used. It is fresh. It is fresh adsorbent. Therefore, it will not contain any solute on its surface. And the meaning of this is capital X0 is 0. So we are supposed to find the quantity of fresh adsorbent that is required per 1000 kg of the aqueous solution. And then we are also supposed to find the minimum quantity of fresh adsorbent that is required or that can be used in this operation. So when it is fresh adsorbent, capital X0 is equal to 0. So let us move on. What would be the approach to solve this numerical? First, we will convert the equilibrium data to the required form. So percentage color removed, it will be converted to color units per kg dry sugar. That is capital Y. And then kg carbon per kg dry sugar, it will be converted to color units per kg carbon, which is nothing but capital X. And if the converted data follows the Freundlich adsorption isotherm, we are going to get an equation for the isotherm in the following form. Capital Y is equal to m into x raised to n. That is, in other words, we are going to get the values of m and n, the second step. And then after that, we will be finding the quantity of adsorbent that is required. And then finally, we will find the minimum quantity of adsorbent that can be used in this case. So simple approach. First, we will convert the equilibrium data to the required form. Then we will check whether the converted equilibrium data is following the Freundlich adsorption isotherm. That is, it is following this equation. And if it is so, we are going to get the values of m and n, the constants. And then then we will find the quantity of adsorbent that can be that is required. First, we will find the quantity of adsorbent that is required, and then we will find out the minimum quantity of adsorbent that can be used in this case. Let us move on. So let us start solving this numerical. As decided, first we are going to change the equilibrium data to the required form. So this is the data that is given to us. So if I have to get this quantity, color units per kg dry sugar, how can I get it? So I can get it in this way. Initial color units per kg dry sugar minus removed color units per kg dry sugar. So color units per kg dry sugar in the solution will be equal to initial color units per kg dry sugar in the solution minus color units per kg dry sugar in the solution that are removed. So that's why we have this equation. Color units per kg dry sugar is equal to initial color units per kg dry sugar minus removed color units per kg dry sugar in the solution. So if you look at this two readings. So you have this 0.005. That is when you are adding 0.005 kg carbon per kg dry sugar, then percentage color removed is 47. That is 47% of the initial color it gets removed. That is the color left per kg dry sugar in the solution. For this case, it's 53%, 100 minus 47. So in this case, when 0.005 kg carbon per kg dry sugar is added to the solution, 47% of the color is removed. So therefore, color units per kg dry sugar in the solution will be equal to 20 minus 0.47 into 20. So these are the removed color units, and if you subtract those removed color units from the original color units, you will be getting color units that remain in the solution, color units per kg dry sugar. So therefore, color units per kg dry sugar will be 20 minus 9.4. This is 9.4. That is color units per kg dry sugar. It will be 10.6, and this is nothing but capital Y. So in this way, we have to get capital Y for all the values. So you have to get it for 0.01, which removes 70% of the color. And similarly, you have to get for the other readings. Let us move. So I have done the calculations, and now I am collecting the results. So kg carbon per kg dry sugar, it is given to us. Percentage removal of the color, it is given to us. And from that, we are going to get color units per kg dry sugar, which is nothing but capital Y. So these values are given to us. These values are given to us. We have understood how to get color units per kg dry sugar for the first case. Initially, the color unit, the concentration of color is 20 color units per kg dry sugar. So if 47% gets removed, it will be 20 minus 0.47 into 20, which is 10.6. If 70% color gets removed, the remaining would be 20 minus 0.7 into 20, which is 6. Then if 83% is removed, the remaining color units will be 20 minus 0.83 into 20, that is 3.4. And accordingly, for 90% removal, the color units left in the solution would be 2. And for 95% removal, the color units will be 1. So in this way, we have converted, or we have got all the values for capital Y. Now you just look at this, the red color rectangle. So here I am moving from 0 to 0.005. In other words, I am adding 0.005 kg carbon per kg dry sugar to the solution, and this is resulting in color reduction from 20 to 10.6. Now let us use this information. We are going to use this information to get capital X. So kg carbon per kg dry sugar, if it is increased from 0 to 0.005, color units per kg dry sugar, it reduces from 20 to 10.6. So that is color units adsorbed per kg dry sugar would be the difference between these two. So original color units is 20. Now the color units remaining after adding 0.005, it is 10.6. So that means the difference of this two is adsorbed on the surface of the adsorbent. So therefore, color units adsorbed per kg dry sugar, it will be 9.4. So I hope you are understanding this. Now let us continue with this. So you have color units adsorbed per kg dry sugar for this values or this row. Color units adsorbed per kg dry sugar is 9.4. Now this is achieved when you add 0.005 kg of carbon per kg dry sugar. So I can take this ratio. Color units adsorbed per kg dry sugar, which is 9.4, divided by kg carbon per kg dry sugar, which is 0.005 in this case. So it will be 9.4 divided by 0.005. So this becomes color units adsorbed per kg carbon. Kg dry sugar and kg dry sugar, they will be getting cancelled out. So we will be left with color units adsorbed per kg carbon, and this ratio comes out to be 1880, and that is nothing but capital X. It is nothing but capital X. So in this way, we have to get capital X. And now we will be getting the remaining values of X in the same way. Let us move ahead. So we got kg carbon per kg dry sugar, then color units per kg dry sugar, that is capital Y. And we will be getting color units per kg carbon, which is capital X. So these values are given to us, and these are the values that we have obtained from percentage color removal. So initially, when you have no carbon is added to the solution, so color units per kg carbon, there will be no adsorption. Then for this reading, when you are adding 0.05, the color is reducing from 20 to 10.6. So color units per kg carbon will be 20 minus 10.6 divided by 0.05, which is 1880. We have understood this just now. And in the same way, we can get for the other values, or we can get other values of X. So this is 20 minus 6 divided by 0.01, 1400. Then 20 minus 3.4 divided by 0.015, that is 1106.67. Then 20 minus 2 upon 0.02, it is 900. And finally 20 minus 1 divided by 0.03, which is 633.33. So now you have all the values of X, and then we have all the values of Y in this column, and we have all values of X that are in equilibrium with the Y values. So in this way, we have converted the given data to capital Y and capital X. So now I will collect all the values. So these are the values for capital Y. So initially it is 20, 10.6, 6, 3.4, 2 and 1. And then color units per kg carbon, we have this values. So now we are going to plot. First, what we will do, because one of the tasks that we have to do in this case is to find the minimum quantity of adsorbent that can be used. So for that, first let us check what is the nature of the equilibrium curve. That is, whether it is a straight line or whether it is concave upward or whether it is concave downward, because that will decide the location of the pinch point that is required for finding minimum quantity of adsorbent that can be used. So for that, we will be plotting the equilibrium values of X and Y to get the equilibrium curve. Let us do that. So plotting of the equilibrium diagram. So I will be plotting capital X on the X-axis. So the scale I have chosen is 1 centimeter is equal to 250. And on the Y-axis, I will be plotting capital Y. The scale is 1 centimeter is equal to 0.5. So if I plot the graph, I get a curve like this. And you can easily conclude that the equilibrium curve is concave upward. It is concave upward. And once it is fixed that the curve is concave upward, now we know how to locate the pinch point. How to locate the pinch point and get the minimum quantity of adsorbent that can be used in this operation. Let us move ahead. So once again, let me tell you, I have solved the same numerical graphically in part number 19. I am giving link to the entire playlist of my videos on adsorption. You please watch part number 19 and learn how to solve the numerical graphically. Okay, so now our conclusion is the equilibrium curve is concave upward, and we will use this information for locating the pinch point. Let us move ahead. Now, after we have converted the equilibrium data, now next task is we have to check whether the given equilibrium data or the converted equilibrium data, it follows the Freundlich adsorption isotherm. So the required form in this case is capital Y is equal to m into capital X raised to n. And the task in this case is to get the values of m and n. How are we going to get that? For that, we will take logarithm on both the sides of this equation. So it will be ln of y is equal to ln of m into capital X raised to n. In the next step, I will use logarithmic identity. Ln of a into b is ln of a plus ln of b. So likewise, ln of m into x raised to n is ln of m plus ln of x raised to n. Then in the next step, I will use another logarithmic identity, which is if ln of a raised to b is b ln of e. So I will use this logarithmic identity. Let me just erase it. So that is y, that is ln of y is equal to ln of m plus n ln of x. And if I write it in a different form, it will be ln of y is equal to n into ln of x plus ln of m. So if you look at this equation is an equation of a straight line. Straight line. What type of straight line? The straight line that will be obtained if you plot ln of y on the y-axis and ln of x on the x-axis. So this equation will be a straight line that will have an intercept on the y-axis. In this case, slope of the straight line is n. So if you could plot a straight line and get the slope, and the slope is nothing but n, one of the constant that we are going to find. So slope of the straight line will give us n, and the intercept will give us ln of m, and from that you can get the value of m and n. So the task is, we will plot this graph. For that we need to get values of ln y, and then we need to get values of ln of x, and then we will be plotting it. If we get a straight line that will make an intercept on the y-axis, we will conclude that the converted equilibrium data is following the Freundlich adsorption isotherm. So let us move ahead. So next task is, we are going to plot this graph. So for that we need to get the values of ln of y and ln of x first. So I have prepared this table. I have collected all the values of y that we have obtained, and forget about the first row because ln of 0 is not it is not definite. So that's why we are starting at the second value. So I get ln of y. Then we have different values of x that we had obtained, and then we will be getting ln of x. Okay, so in the graph will be obtained by plotting this values of ln of y against values of ln of x. So that I will do on next. I will do that. So the graph will be plotted like this. In this case, we will be getting the intercept on the negative side of the y-axis. So that's why I'm showing this graph. So the scale is on the x-axis, 1 centimeter is equal to 1, whereas on the y-axis 1 centimeter is equal to 2. And if I plot ln of y on the y-axis and ln of x on the x-axis, I will be getting a graph which is a straight line. And what I'll do, I will extend it so that I get the intercept on the y-axis. So a plot of ln of y versus ln of x is a straight line, and it has an intercept on the y-axis. So our conclusion is, the graph is a straight line with an intercept on the y-axis. So we can conclude that, therefore, the adsorption follows the Freundlich adsorption isotherm. Now we have to get the constants. So first of all, we will get the slope. So for getting slope, I am considering this point. Any 2 points you can consider. I am considering this point. This point, it has coordinates of 3.6 and minus 6.4, and I will consider another point over here. This point has coordinates of 2 and minus 10. So now I can get the slope. So slope is y2 minus y1, that is minus 6.4 minus 10 divided by x2 minus x1, that is 3.6 minus 2. So therefore n is equal to 3.6 divided by 1.6, and that is n comes out to be 2.25. So slope of the straight line is 2.26, and slope in this case is nothing but the constant n. Then intercept in this case is intercept on the y-axis, it is minus 14.40, and then that means m is e raised to minus 14.40. That is m comes out to be e raised to minus 14.40 is 5.57 into 10 to the power minus 7. So in this way we have got the values for the two constants. Why we have done that? Because once we get the straight line, we have concluded that the converted equilibrium data, it is following the Freundlich adsorption isotherm. So the equation for the Freundlich adsorption isotherm, it is of this form: capital Y is equal to m into capital X raised to n. We got n as 2.25 and m as 5.57 into 10 to the power minus 7. So that means we have got an equation for the Freundlich adsorption isotherm, which is capital Y is equal to 5.57 into 10 to the power minus 7 into x raised to 2.5. So that completes this task. We have got an equation for the Freundlich adsorption isotherm after getting the values for n and m. Let us move ahead. Then we have to get the quantity of fresh adsorbent that is required in a two-stage operation, two-stage countercurrent adsorption operation. So I have shown, for your understanding, I am showing the operation. So these are the two stages. Feed solution is entering in stage number 1, whereas adsorbent is added to stage 2. Then it will move throughout the operation, and then the liquid solution will be moving in this direction. That is the two phases, they are moving counter current to each other. Now the operating line equation, which I had derived in in part number 18, I am giving link to the entire playlist in the description section. So in part number 18, I had derived this equation for two-stage operation. For two-stage operation, the equation for the operating line will be y0 minus y2, capital Y0 minus capital Y2 upon capital X1 minus capital X0, that is equal to SS upon LS. Now, in this case, if you look at first stage, what do you understand? So this is the liquid phase that is leaving stage number 1, and this is the adsorbent phase that is leaving stage number 1. And in our discussion, we are assuming this stage to be an equilibrium stage, which means that the leaving phases, they are in equilibrium with each other. So in this case, capital Y1 is in equilibrium with capital X1, or capital X1 is in equilibrium with capital Y1. So as X1 is in equilibrium with Y1, it should follow the equilibrium relationship. The Freundlich adsorption isotherm, the equation is nothing but the equation of the equilibrium curve. You need to understand that. Equation for the Freundlich adsorption isotherm is the equation of the equilibrium curve. The equilibrium curve that we have drawn, the equilibrium curve which is concave upward. And since X1 and Y1, they are in equilibrium with each other, those two values should satisfy the equilibrium relationship. So that's why you get this equation. Capital Y1 is equal to 5.57 into 10 raised to minus 7 into X1 raised to 2.25. Now y1 is obtained by solving this equation. What is that equation? Capital Y0 upon capital Y2 minus 1 is equal to capital Y1 by capital Y2 raised to 1 by n into capital Y1 by capital Y2 minus Y1. Now what is this equation? This equation is obtained when you apply the Freundlich adsorption isotherm to a two-stage counter current operation. This equation I have derived in part number 20. You please refer part number 20. In that discussion, I had discussed how to get this equation. So over here, I am directly using the equation. When I use this equation, that means I am applying the Freundlich adsorption isotherm to this two-stage counter current operation. Let us move ahead. So Y0 is known to us, it is 20. Y2 is known to us, the final Y, which is 2.5% of 20, which is 0.5. N we obtain, it is 2.25. So if I use the values, it will be 20 upon 0.5 minus 1, that is equal to capital Y1 divided by 0.5 raised to 1 upon 2.25 into Y1 by 0.5 minus 1. So if I simplify, 20 upon 0.5 is 40 minus 1, 1 upon 0.5 is 2, so it is 2 into capital Y1 raised to 0.44, 1 upon 2.5 is 0.44 into 2 into capital Y1 minus 1. So you get this equation. Therefore, 40 minus 1 is 39, so that will be 2 into Y1 raised to 0.44 into 2 into Y1 minus 1. So we got this. 39 is equal to 2 into capital Y1 raised to 0.44 into 2 into capital Y1 minus 1. That is 39 is equal to 2 into capital Y1 raised to 0.44 into, I am multiplying this term inside this bracket. So 2 into capital Y1 raised to 0.44 into 2 into capital Y1 minus 2 into capital Y1 raised to 0.44. So that is 39 is equal to 2 into capital Y1 raised to, you have the same base, so it will be 2 into capital Y1 raised to 0.44 plus 1 minus 2 into capital Y1 raised to 0.44. That is 39 is equal to 2 into capital Y1 raised to 1.44 minus 2 into capital Y1 raised to 0.44. That is 39 is equal to 2 raised to 1.44 into capital Y1 raised to 1.44. I have separated the power. Same thing I have done over here. Minus 2 raised to 0.44 into capital Y1 raised to 0.44. That is 39. 2 raised to 1.44 is 2.71. 2.71 into Y1 raised to 1.44 minus 2 raised to 0.44 is 1.36. So 1.36 into capital Y1 raised to 0.44. And then I have rearranged it in this way. So 2.71 into capital Y1 raised to 1.44 minus 1.36 into capital Y1 raised to 0.44 minus 39 is equal to 0. So we have an equation in capital Y1 and we are supposed to solve it to get Y1. If you have to get Y1, we will have to solve it. And what we will do, you can use any method to solve this equation. In my discussion, I am going to use Newton-Raphson method to get to solve this equation. So for that, I am letting f of y1 to be this equation. So f of y1 is equal to 2.71 into y1 raised to 1.44 minus 1.36 into y1 raised to 0.44 minus 39. And objective is to solve f of y1 is equal to 0. The Newton-Raphson method is, the formula for Newton-Raphson method is, you can get new value for y1. I am denoting the new value as y1 n plus 1. You can get it by using old value. The old value in this case is y1 n. So the formula is y1 n minus the function evaluated at the old value divided by derivative of the function evaluated at the old value. So we have the function f of y1 is equal to 2.71 y1 raised to 1.44 minus 1.36 into y1 raised to 0.44 minus 39. In order to solve f of y1 is equal to 0, the Newton-Raphson method is used, as I told you earlier. The equation is, the formula is y1 n plus 1 is equal to y1 n minus f evaluated at y1 n divided by f dash evaluated at f y1 n. So we need the derivative of the function. So f dash of y1 is equal to 2.71. Derivative of this function is 1.44 into y1 raised to 1.44 minus 1 minus 1.36. Derivative of this function is 0.44 into y1 raised to 0.44 minus 1, and derivative of constant is 0. So therefore f dash of y1 will be 3.90. This is 3.90. y1 raised to 0.44. 1.44 minus 1 is 0.44. And this multiplication is 0.6. So it is minus 0.6. y1 raised to 0.44 minus 1 is minus 0.56. So in this way, we have got the derivative of the function. And now let us move ahead. Let us use the Newton-Raphson formula for solving the equation. So we have the function f of y1 is equal to 2.71 y1 raised to 1.44 minus 1.36 y1 raised to 0.44 minus 39. We got the derivative. F dash of y1 is 3.90 y1 raised to 0.44 minus 0.6 y1 raised to minus 0.56. Now the formula to be used, and the formula for Newton-Raphson method is y1 n plus 1 is equal to, that is new value of y1 is equal to old value of y1 minus function at the old value, function evaluated at the old value divided by derivative evaluated at the old value. So you can start with a guess, as we have to do while using Newton-Raphson method. We have to start with a guess, and the guess that I am using is, I'll say that the color concentration, it is reduced to half after the first stage. So that means the initial guess y10, the initial starting guess is 10. You can use a different one, no problem, but I am using a simple approach. The color concentration gets reduced by 50% at the end of first stage. So for me, the initial guess is y10 is equal to 10. So I will have to calculate the function at this guess value, that is f of y10, that is 2.71 into y10 raised to 1.44 minus 1.36 into y10 raised to 0.44 minus 39. And when I use the value of y10, it will be f of y10 is equal to 2.71 into 10 raised to 1.44 minus 1.36 into 10 raised to 0.44 minus 39. And that gives me f of y10 as 31.8938. So if I solve it, if you solve this equation, the function at y10 will be coming to be 31.8938. Now similarly, we will get the function, derivative of the function at y10. So f dash of y10 will be equal to 3.90 into y10 raised to 0.44 minus 0.56 into y1 raised to minus 0.56. So that is f dash of y10 is equal to, if you put the values, if you use or let me just say f dash of y10 will be equal to 3.9 into 10 raised to 0.44 minus 0.56 into 10 raised to minus 0.56. And if you solve this, you are going to get f dash of y10 as 10.5762. And then the next value, new value for y1, which I am denoting after 0, I will be getting 1. So new value of y11 will be obtained by using the old value. So y10 old value minus function evaluated at the old value divided by derivative of the function evaluated at the old value. So y11 will be equal to 10 minus 31.8938 divided by 10.5762. That is y11 comes out to be 6.98439. So first iteration, when I use the guess value, I get a new value for I1. And in the next step, I will be using this value to get new value for, now in the next step, y11 will be my old value. And I will be getting new value for y1. So I will have to do this until I get a constant value for y1. And once that happens, we have arrived. You can conclude that we have arrived at the solution. So let us move ahead. So I have used the function and the derivative and then the Newton-Raphson method formula. And then I have done this iterative calculations. I am taking all those calculations. I have explained the first step, first iteration to you. You just have to follow the same steps until you get a constant value for y1. You can understand it. So let us, y1 n represents the old values, then f evaluated at y1 n, then you have f dash evaluated at y1 n, and finally you get the new value by using the Newton-Raphson formula. So initially the calculations which I have shown, old value, initial guess value is 10, for that the function is 31.8938, derivative of the function is 10.5762, and the new value of y1 that we get is 6.98439. You have understood this. Now in the next step, I will be using this as the old value. So 6.98439. So if I use this as the new and the old value, the function at this old value comes out to be 2.31721. The derivative of the function comes out to be 8.97032. And then after using this formula, the new value for y1 I get is 6.72607. Next, this will be the old value for the next step. So with this old value, I get the function at that old value, then derivative of the function at that old value, and then new value for y1. In the next step, this will be the old value. The function at this value is this. Now we are coming closer, we have come closer to 0. At the exact value of y1, this function becomes 0, you know that. And then the derivative of the function at this value is 8.8139, and the new value is 6.72398. That means you are getting the same value for y. So now y1 is becoming constant. We are coming close to the solution. Then in the next step, I'll use this as the guess value with the additional digits. I have not considered the additional digits over here, but with this value, the function is almost 0. That is, we have arrived at the solution. The derivative of the function is again the same thing. And y1, the new value for y1 again remains the same, 6.72398. So in this way, we have some additional digits, but as you can check for yourself that after this step, you are going to get a constant value for y1. So our conclusion is the value of y1 that can be obtained by solving the equation is 6.72398. So in this way, we have got the value of y1. Let us move ahead. So y1, we got 6.72398. Now you must have understood how we got that. As x1 is in equilibrium with y1, I have talked about it. Y1, capital Y1 will be 5.57 into 10 to the power minus 7 into x1 raised to 2.25. That is 6.72398. We have got that value. Now we are getting x1. So 6.72398 is equal to 5.57 into 10 to the power minus 7 into x1 raised to 2.25. That is 6.72398 divided by 5.57 into 10 to the power minus 7 is equal to x1 raised to 2.25. That is x1 raised to 2.25 is equal to 120,71777. This division is 120,71777. That is x1 is equal to 120,71777 raised to 1 upon 2.25. That gives us x1 as 1404.281. So you please do one thing. You compare this value with the value that was obtained in part number 19, where I had solved the numerical graphically. We'll come to know that we are getting almost the same value, 1404.281. Now we will use the equation of the operating line to get the quantity of adsorbent that is required. So equation of the operating line is y0 minus y2 upon x1 minus x0, that is equal to SS upon LS. So y0 is 20, we know that. Y2 is 0.5, we know that. X0 is 0, we know that. Why x0 is 0? Because we are using fresh adsorbent. That's why x0 is 0. LS is 480, we had understood it earlier. So if I use these values, I will be getting 20 minus 0.5 divided by 1404.281 minus 0, that is equal to SS upon 480. That is 19.5 divided by 1404.281 is equal to SS upon 480. That is 0.0139. This comes out to be 0.0139 is equal to SS upon 480. That is SS is equal to 0.0139 into 480. That is SS is equal to 6.672 kg. And that is the quantity of adsorbent that is required in a two-stage counter current operation. Again, you can compare this value with the value that was obtained in part number 19, where I had solved the numerical graphically. So in this way, we complete this task, the task of getting the quantity of fresh adsorbent that is required in the operation. Okay, now let us get let us complete the last task. What is that? To find the minimum quantity of adsorbent required. Now we have understood that the equilibrium curve is concave upward. So if the equilibrium curve is concave upward, then we know that the pinch point, the operating line will be drawn like this, and the pinch point will be located over here. So if the curve is concave upward, and here in our case the curve is concave upward. So this point, coordinate of this point is y0 and coordinate of this point is x1 max, the maximum possible x1 that can be obtained. It is possible when you are using minimum quantity of adsorbent. So now the objective is get x1 max and use x1 max to find out the minimum quantity of adsorbent required. So the equilibrium curve and the operating line, they intersect each other at the pinch point, at this point. And what are the coordinates of this pinch point? x1 max, y0. Therefore, the pinch point, this point, satisfies the equation of the equilibrium curve. What is the equation of the equilibrium curve? Y is equal to 5.57 into 10 to the power minus 7 x raised to 2.25. So therefore, y0 is equal to 5.57 into 10 to the power minus 7 into x1 max raised to 2.25. So y0 is known to us, and then you can get x1 max. And once x1 max is obtained, you can find the minimum quantity of adsorbent that is required. Y0 is 20, we know that. So y0 will be equal to, we have this equation, y0 is equal to 5.57 raised into 10 to the power minus 7 into x1 max raised to 2.25. y0 is 20. So therefore 20 is equal to 5.57 into 10 to the power minus 7 into x1 max raised to 2.25. That is 20 upon 5.57 into 10 to the power minus 7. That is equal to x1 max raised to 2.25. That is x1 max raised to 2.25. And this quantity is 35906643. That is x1 max will be equal to 35906643 raised to 1 upon 2.5. That gives us x1 max as 2279.583. So once x1 max is known to you, the next task would be to use the equation of the operating line, equation of this operating line, to find its slope. And the slope, from the slope you can get the quantity of minimum quantity of adsorbent that can be used. Let us move on. So the equation of the operating line, y0 minus y2 upon x1 minus x0, that is equal to SS upon LS. But if x1 is x1 max, S will be SS minimum, the minimum quantity of adsorbent. So therefore y0 minus y2 upon x1 max minus x0, that is equal to SS minimum upon LS. Only SS minimum is unknown. You just have to solve that. So in this case, we have this y0 minus y2 upon x1 max minus x0 is equal to SS minimum upon LS. So y0 is 20, y2 is final y, which is 0.5, that is known to us. X1 max is, we just got the value, 2279.583. X0 is 0. Why? Because we are using fresh adsorbent. So LS we know that we had done this calculation earlier. It is 480 kg. So therefore you have 20 minus 0.5 divided by 2279.583 minus 0. That is equal to SS minimum by 480. That is 220 minus 0.5 divided by 2279.583 minus 0 is equal to SS minimum upon 480. That is 19.5 divided by 2279.583 is equal to SS minimum by 480. That is 0.008554. This is 0.008554. That is equal to SS minimum by 480. That is SS minimum is equal to 0.008554 into 480. That is SS minimum is equal to 4.11 kg. So in this way, we get the minimum quantity of adsorbent that can be used in this operation. And with this, we complete all the tasks. We have converted. We have obtained the equilibrium data in the required form. We have checked that whether we have found that the converted equilibrium data is following the Freundlich adsorption isotherm. And then we have got the equation for the Freundlich adsorption isotherm. We have got values for M and N. Then we obtained the quantity of adsorbent that is required in the operation. And finally, we have obtained the amount of the minimum quantity of adsorbent that can be used in the operation. So with this, I will end my discussion. I will end my discussion for this video lecture. I hope you have learned how to apply the Freundlich adsorption isotherm and get the quantity of adsorbent required, and also to get the minimum quantity of adsorbent that can be used. So with this, I will end today's discussion. Thanks for watching my video lecture. Do subscribe to my channel. Tell your friends to subscribe to it and hit the bell icon so that you will be notified as soon as I upload any new video on my YouTube channel. For now, thank you. Have a nice day and hope to see you soon in my next video lecture. In my next video lecture, I'll be solving one more numerical that is based on application of Freundlich adsorption isotherm. So thank you. Have a nice day. Bye.